Okay, in lesson 5 we're going to concentrate on Diels-Alder reactions. When it comes to Diels-Alder reactions, truthfully, a lot of us really don't know for sure what's totally going on in this reaction. We have a lot of molecular orbital explanations for determining sort of what's going on, but in reality, it is the case that we don't necessarily know 100% of what's going on. So I'm going to begin this reaction by showing you something that's not 100% correct, and I know that, okay? I'm first going to take a conjugated diene. This is what's referred to as the S trans position. We've got a single bond right here, double bond, double bond. That single bond can rotate. That would give me the S cis position. Okay, so this is my diene in an S cis position, which we'll talk about the importance of that in a minute, okay? I'm going to put him right here. Imagine this is like a double date. Now, here's why 3 is a crowd. And I want you to pay no attention to the green-blue matrix because that's the biggest thing that's wrong here. In comes another alkene, okay? Let's call him dienophile. He's a third couple. And when he comes into the mix, here's what happens. This, say girl here and this guy here decide, ooh, I like you better than who I'm with. I want to go with you. And down here we have the same type of thing happen and go, well, that's okay, I like that one better over here. And bam. And what happens there is we end up making new bonds between these red atoms over here and these black atoms over here. Which means that in the back we're stuck with some p orbitals that are like, well, I think we just got left too, and I think that we should stay together, okay? So that's what's going to make another pi bond is something back here. Now, that looks like a lot of crazy if you haven't looked at this reaction yet. So let me show you what the actual reaction looks like here. Okay. So in the Diels-Alder, we have a diene, so that's going to be a conjugated diene, and a dienophile. And what happens on paper, this is not necessarily the right way to represent this, but this is sort of how we have to represent a mechanism in this case. In truth, as I said, there's a lot of molecular orbital theory that's going on here, and it's like things just kind of come together in harmony. But on paper we will say that the electrons from this double bond move over to form a new bond between this carbon and this carbon. This double bond moves back, and this double bond moves over to form a new sigma bond between this carbon and this carbon. So our new couples, our new bonds are here, here, and then the third one is back here because that's our new pi bond. Which means that basically you just connected 2 molecules into one, which is pretty cool. Totally fails entropically, but the enthalpy that's released is actually quite favorable to allow this reaction to happen. So we call this, this sort of behaves like a nucleophile, and this kind of behaves like an electrophile, because electron donating groups are going to speed up the reaction if they're on the diene, and electron withdrawing groups speed up the reaction if they're on the dienophile. The really cool thing about this reaction is that it does a lot of really neat stuff. Okay, so if you have a diene that's reacting with an alkyne, instead of getting 1 double bond in your cycle, you actually get 2. So again, we're taking the pi electrons, moving down, moving up, moving over, and that's going to make the new bonds here, here, and here. This bond, on the other hand, let's say, arbitrarily, that one, remains because it's not going to be affected in this movement, right? We're only using one pair of electrons to move them down. If that's an easier way to look at it, then feel free to look at it that way. Okay. As I was just saying, your diene, in order to react, has to be in what we refer to as the S-cis position. So that diene has a double bond in the middle. Sorry, let me redraw that for you. And in the center there, that single bond can rotate, right? Well, obviously, most of the time it's going to be in this formation if it's left free to rotate. That means that in order for this reaction to happen, first you have to have the molecule rotate into the proper orientation. There's some more cool things that it can do. If you have a diene come in contact with a cis alkene, your R groups are cis to one another, then you get only cis cyclohexene rings as your products. Okay, the R groups stay cis to one another. If instead you have a trans, same thing happens except that you end up with trans R groups in both of your products. And both stereoisomers there can happen. Okay, what I refer to as the party hat reaction. I kind of like this. It's still DielsAlder. But you've got a 5-membered ring dienophile. This guy, when placed with an R group, basically your dienophile, the only difference in this guy and these, he's already in the right position. He's in an S-cis position. This seems to be the hardest thing to see, is that carbon right there ends up going upwards. So let me show you what that means. If you look at the 5-membered ring as the product over here, we've got here our sp2 carbons. So those would be the ones that are here and here. We've got these 2 carbons, which would be here and here. And then we've got this little guy that shoots upwards. So let me show you what that is. He shoots up like that. And the reason why he shoots up is because here's what originally was my dienophile. I just want to show you what this looks like on a model. And yes, it's a little bit sterically hindered, okay? So here's what we've got. Get my fingers out of the way. These are my sp2 carbons in the back. The black carbons, as you can see from the top, are the 5-membered ring that you originally started with. So we actually have a 5-membered ring from that direction. We have a 5-membered ring from this direction that consists of 3 of the black ones, 2 of the red. And on the underside, you can see that that's actually a cyclohexene ring. Well, when you have an R group on the dienophile, you have to determine where it is that that R group is most likely to occur in the products. So if we look at 2 different options here, we could either put our carbon up here, right? That would be one position. What I see as a problem here, though, is that these hydrogens are kind of bumping into each other. So more likely is a situation where you have the carbon down here. I want to make sure you can still see this okay. Okay. And the reason for that is that down here we don't really have the steric hindrance that we have up here. There's much more room. We refer to this as the endo position because it's inside this ring, the 6-membered ring that's sort of formed on the bottom. And this is the exo position because it's trying to get on the outside of that ring. Okay. The endo position is quite a bit lower in energy to form, And there's reasons for that with the transition state in addition to the actual product. But we'll just go with it as a general guide for now. Okay, there are special cases. If you look into more detail on a DielsAlder reaction. So if we look at reacting this type of compound with this type of compound, there's two different things that could happen. You could end up with the NH and the COOH close to each other, or you could end up with them in another type of direction. This would happen because one of these has flipped. So in other words, your R group has aligned to a different direction. In order to look at which one is most favorable, and what we do find is that this is the major product, we have to look at the electronic signatures of both of those. Let's look at the resonance structures. So here, electrons could come down, over, and down, and that would be a good resonance structure for that molecule. The resonance structure for this molecule, we could flip these electrons up, and you end up with this type of arrangement. Well, this actually is favorable for a reaction to happen, because if you look at the hybrid between these two, that means that this carbon is really partially positive. And the hybrid here would mean that this carbon is partially negative. Well, that's like easy, right? Because positive goes to negative, or negative goes to positive, whichever you want to consider it. So that means that the negative and positive will come together to form a bond more easily than if it was not the case like that. So if you were to flip that molecule, for example, this direction, that would put a carbon here that doesn't really have a charge on it, reacting with a negative charged carbon, and that's just not as good of a match. And same thing here, we have a carbon that's not really electronically in tune with this one. That's the reason why this is the transition state that will work more easily, and this is the major product. Again, this is more detail oriented in the DielsAlder reaction, and may not be something that you see every day. Okay, hope to see you in class. Thanks, bye.